What's up, everyone? In this video, we're going to prove the following. For all primes p greater than or equal to 5, we want to show that p squared is congruent to 1 mod 24. In other words, we want to show that p squared minus 1 is a multiple of 24. And of course, since we have already talked about modular arithmetic in last video, we're going to show it in two different ways. And if you don't know what modular arithmetic is yet, or didn't watch the previous video, go check it out first. So here we go. So let's start with the proof without modular arithmetic. Meaning, we just want to simply show that p squared minus 1 is a multiple of 24. Well, how do we do this? We actually need to have one theorem that is very basic in number theory that says if an integer n is a multiple of some prime numbers p1 and also multiples of some other prime numbers p2, where p1 and p2 are different, then it has to be a multiple of the product of p1 times p2. So let's suppose that this is true first. How are we going to show this? Well, we also can rewrite this idea by raising it to some powers. Let's say this is k1 and k2 power, meaning as long as n is divisible by two different numbers, where those two numbers only have the common denominator 1, then we can claim that the number n is going to be a multiple of the product of what it can be divided by. So in this case, let's consider the denominator or the divisor 24. We can rewrite 24 as 3 times 8, which is the same as 3 times 2 to the third power. Then here we know that 2 and 3 are relatively prime. In other words, the only common denominator or the only common divisor or factor between 2 and 3 is positive 1. So with the last theorem that we just talked about, we can now rewrite our statement into the following form. In order to show that p squared minus 1 is a multiple of 24, it is sufficient to show that p squared minus 1 is a multiple of 8 and p squared minus 1 is a multiple of 3. And keep in mind, in this case, we will have the condition that p is a prime number that is greater than or equal to 5. In other words, p is already known that cannot be a multiple of 3 or 2 at all. So using the fact that p is not a multiple of 2 nor 3, in other words, p is not even 2 nor 3, we can just do the following. Since p is not a multiple of 2, we know that p must be in the form of 2k plus 1, right? Because if p is not a multiple of 2, it means that it has some remainder. And the only option that we have is when the remainder is 1. Good. So in this case, we're going to do a substitution. We actually get that p squared minus 1 is now equal to, let's see, 2k plus 1 quantity squared minus 1, which is 4k squared plus 4k plus 1 and then minus 1 are cancelled out. So we can now factor out the 4 and the k, giving us 4k times the quantity k plus 1. So in this case, we know that this p squared minus 1 must be a multiple of 4, as we have k times k plus 1 is of course an integer. So we have 4 times some integer, meaning that it has to be a multiple of 4 by definition. Moreover, if we consider the second part, k times k plus 1, we are going to show that this product right here is also even, meaning it is also a multiple of 2. How? Well, since k is an integer, we have two options. If k is even, then k can be written as 2 times some m. In other words, we have 2 times some integers, so we're done. We just show that k times k plus 1 is even, or is a multiple of 2. Good. What if k is odd? Then if k is odd, we can say that k could be some 2m minus 1, so that the term k plus 1 is going to turn into 2m plus minus 1 plus 1, and the minus 1 plus 1 cancels out, giving us 2m. Meaning that this product, k times k plus 1, is also an even number. It's a multiple of 2. So we check that. Therefore, this product here is always an even number, meaning that it is a multiple of 2. Then we're going to multiply by 4, implying that the whole term is a multiple of 8. Good. Since we show that p squared minus 1 is a multiple of 8, we just finished our first part of our proof. Then move on to the second part. We will do something similar. Since p has to be a prime number that is greater than or equal to 5. In other words, p cannot be equal to 3, where p as a prime number, the only option that p is a multiple of 3 is 3 itself. So we now ending up with two results. We have case 1. P is some multiples of 3 plus 1, meaning that p has a remainder 1 after dividing by 3. Then we see that p squared minus 1 is, we can actually factor it out because we have a difference of squares, giving us p minus 1 times p plus 1. Then substitute in our condition. We see that in this case, the first term, p minus 1, is going to be reduced down to 3k, implying that it is a multiple of 3. Then for the second case, suppose p is congruent to 2, or in other words, it is some multiples of 3 plus 2, meaning the remainder is 2. Then we also get p squared minus 1 is certainly p minus 1 times p plus 1. And this time, for the second term here, this will turn into 3k plus 3, and we can factor out the 3, ending up with 3 times the quantity k plus 1. In other words, because of the second part, we can claim that this product is also a multiple of 3. Like this. And if we combine the two cases, we just show that no matter what p we choose, as long as p as a prime number is greater than or equal to 5, this statement, p squared minus 1 is a multiple of 3, actually is valid. Excellent. So now, since we just show that p squared minus 1 is a multiple of 2 cubed, which is 8, and also a multiple of 3, now we can just combine it back and say that p squared minus 1 is a multiple of the product of 8 times 3, which is 24. So we just finished our proof. Next, let's move on to the other method, which is using modular arithmetic. So if we're going to use modular arithmetic, this is what we need to consider. Since p is a prime number that is greater than or equal to 5, in other words, we want to list out all the possible numbers between 0 to 23 that are relatively prime to the number 24, the modulus 24. And that we want to make sure that we're not going to include p equals 2 or p equals 3. Okay, so if we consider the numbers from 0 to 23, again, is 1 less than the modulus. The numbers that are relatively prime would be 1, 5, 7, 11, 13, 17, 19, and 23. So it means that we just need to check these 8 numbers and substitute in to see if we'll be able to get the statement p squared is congruent to 1 mod 24. Then we are going to get this. We're going to make our table, and we just need to have 2 rows, p and p squared, where the p numbers could only be one of these 8. We have 1, 5, 7, 11, 13, 17, 19, and 23. And keep in mind, since we're doing modulus, we can also add or subtract the multiples of the modulus in order to play around and make the numbers smaller and easier to manipulate. So in this case, I'm going to subtract 24 for the last 4 terms, meaning that we're going to end up with negative 11, negative 7, negative 5, and negative 1. Why will I do that? Because we're going to square it, and the negative sign will be cancelled out once we square, because negative times negative is positive. So we just actually need to calculate 4 numbers, and then we'll actually get the other 4 right away. So let's jump in. 1 squared is clearly 1. 5 squared is 25. Let me mark it down with purple. And if we reduce it down, it will turn into 1, because divided by 24, we get 1 remainder 1. Next, we have 7 squared, which is 49. And again, if we divide by 24, we get 2 remainder 1. 11 squared is 121. So divide by 24, we get 5 remainder 1. Good. So for the other 4, we also get 1, 1, 1, and 1 each. So it shows that for the possible options of the prime numbers in modulus 4, modulus 24, the square of those numbers must be equal to 1 or congruent to 1, meaning that it satisfies the condition that we want. P squared is congruent to 1 in modulus 24. Therefore, we just prove that p squared minus 1 is a multiple of 24 for all the p's prime numbers that are greater than or equal to 5. And that is it. So in this example, we actually see that using modular arithmetic can help us quickly to find out the answers, especially when there are only finitely many terms. But of course, if we want to understand the logic behind it, the fundamental way of proving And number 3 problem is also important. By setting up the correct cases, we'll be able to show that why it works for each situation. That's it. Hopefully you enjoyed this video, and if you think this video is cool, don't forget to like and subscribe, and also check out my other videos. And if you have any comments or thoughts or ideas, don't forget to leave your comment below. So I'll see you in the next video.